knowledge as much as possible to see how we can like use it later. So that's, I mean, like my interest to get into this workshop. And yeah, for sure, it's nice to meet all of you. Thank you.
Thank you, Zivor. Nice to meet you too. And please tell me how familiar you are with Python and AI.
Yeah, like I used Python like in 2012 and 2013. And also I use the JavaScript and C# for Unity because I built also an application. So I was familiar, I mean, like to use the Python script also in Grasshopper. But since then, I mean, like I use it often, like not like too much because I'm more like with Grasshopper. So I mean that's I mean like my experience now. I mean since 2013 till now, and just like is about the Grasshopper. If I need like to make a script, I mean in Python for sure I can make it, but not like too much as before. That's how is it now? Yeah.
So you know lots of programming languages like JavaScript, C#, Python. That's good.
Yeah.
Okay. Let's move on to Lorena. Lorena, please introduce yourself and let me know you.
Hello, everyone. I'm Lorena from Federal University of Bahia, Brazil. I'm also academic coordinator here in the Faculty of Architecture. My research area is augmented reality, and I have some students doing some apps in Unity, but I don't have expertise in Python or in any program language. So I'm very happy to be here in this group, and I'm curious about the theme. I don't know. I don't research in this theme about artificial intelligence, but I'm very curious in interested. I don't know if I have time to do the exercise and the practical session, but I'm here to listen and to know more about that. Thanks.
Thank you, Lorena. Nice to meet you. And I think there is, okay, all of us have introduced ourselves, yeah? So we can move on. Okay, nice to meet you all. So we have like 2 people, I think, or 3 people with no Python knowledge, so they are not very familiar with Python. I'm going to through the basics of Python, so our friends can get familiar with Python. But Python is really simple and it is easy to understand, so everyone can understand Python really quick. So let me just have a session on let me I will start my collab and let's go through some basics of Python, but not too much basics because most of you know Python really well, and some of you know some other languages, some programming languages. So let me share my screen. Okay. Sorry, please wait until I make it. I have lots of tabs open, and yes, so that's it. Before we start our workshop, let me say that I will teach you the basics of AI. After that, we are going through the intermediate and advanced levels of AI and deep learning, specifically deep learning, because nowadays most of the talkings are about deep learning and the differences between artificial intelligence and machine learning and deep learning. And after that, we are going to implement some architectures and models that we call StyleGAN 2. It is introduced, I think, in 2019 by Nvidia corporations. So it is a kind of generative adversarial networks. So we are going to get familiarized with that. And I think we need to go through the basics and after that through the advanced materials, because nowadays, as a person like Andrew Ng, who is the professor of Stanford, he's teaching AI and computer science. He's one of the pioneers of AI in the world. He said once I was watching a video on YouTube, and he said that nowadays many people are saying that they are using AI, but when we say what is the how did you use AI in your work and what is the AI here and what's the stuff, they say that, yeah, let me skip it, we don't need to see that, and those kinds of things. And they just don't use AI, they just use the word, and they don't know what is AI. They don't know how it is working and how we can implement these algorithms. So it's better to know the elements of AI, what it is made up of. So, but before that, let's go through some basics Python. And let me share my screen here. And okay. Let me minimize the zoom controls. Okay, zoom controls are really annoying. Can you see my screen?
Yes, yes.
Okay. So Python is an implicit kind of programming language, so it is not like C or C++ or C# or Java. For example, when I said that when I want to initialize a variable like a, I give it a value of, for example, 5. And when I want to print the value of a, I just type print in a parenthesis and type a. After that, in Colab, this is what you see. This is Colab, and I'm on a pro subscription plan. And you should just hit connect button, and it got connected. So it is going to be connected. And there is an extension for Google Chrome and Firefox, as I'm using Firefox here. You can download that extension. It is called Colab Auto Reconnect. So because if you are not an interactive user in Colab environment, Colab will just disconnect you. So it is good to use this extension. So you are not going to be disconnected. So let's get back to the point. And this is like what we say. For example, I initialize a by the value of 5. So when I print the value, so by the and press enter control, and it is going to show me the value. But what if I just hit, for example, my name, and again print the value? So here we have 5, but here we have my name. This is a string. This is an integer. It is a number. It is a whole number. But this is some kind of alphabets and characters. So, but at the end we see that it prints my name as the value here to the console. So it is not, it is what we call implicit programming language. It changes the value of the variable without letting you know. So the first thing here, we have this, but we have other types of values. For example, a number or integer. My integer is, for example, 5, or my a string, for example. Sorry, okay. A string, for example, I will my name, for example, Muhammad, or other kinds of values as Boolean types, my Boolean. So Boolean types just got true or false. It is a binary kind of data type. So we can just set it as true, or we can just set it as false. They cannot get any other kind of types. And there is no limitation in your variable names. As here, I initialized the name by my Boolean. I called it my Boolean. I can call it, for example, picture, and the value is going to be, for example, a Boolean value. The type is Boolean, and the name is picture. So any kind of name you can set it to, but you cannot just set it a number. For example, 9 equals true. It is going to be some kind of it will throw some errors. So you cannot set a variable name to a number. So after that, let me have another cell. This is a cell, and this is a cell. So we can run this independently. For example, I can run this, and I can run this. You can hit this button to run the cell, and you can just press Enter plus Control to run the cell. And for example, I want to just add a number to another number. For example, first number is 5, and second number is 3. And we can just have the addition, the result of the addition of these two numbers. For example, first number, let me just shorten it. Okay, first number and second number, so it is easier to use them because they have really long names. Okay, first plus okay, and we are going to hit enter plus control, enter control, and the result is 8, as you see. What if I just subtract their values from each other? So the result is 2. We can just do this and multiply, and some let's divide them. And we can control the flow of the program we are writing. For example, we have some statements, some conditional statements as if or elif and else. So how we are using to if, elif, and else? Elif is else if, else this, then that. So for example, how it is going to work? When I write if, after that, it needs a condition. So for example, if let's first declare a value of x, for example, 5, and say if x is greater than 3, so print yes, x is greater than 3. So, and let's see the results. Because x is 5 and 5 is greater than 3, because the result of this comparison is going to be a Boolean. So after if, we need Boolean. If it was true, so we know that x is bigger than 3, so it is true. If it is true, then do this, then print x is greater than 3. So, but if it this part was false, this code block was not going to be executed. So, for example, this, nothing is going to be shown here. You see, because the result of this part is false. 2 is not bigger than 3, so the result is false. But we can add something like elif x is bigger than or is greater than 1, print for example, x is between 1 and 3. So let's see the result. And x, is there anything wrong?
X is greater than 1. It should be the same sign as x is greater than 3, right?
Yeah, I think
Line 5.
if elif
or x is less than 1.
I don't know. So let's try with else to see. Else print no, it is not, for example. So it works. Okay, let's say here, for example, 5 and 3, and if x is, for example, smaller than 5, and I'm going to just delete this. If x is smaller than 5, then print x is smaller than 5. So this is how it works. So the first part here, because 3 is smaller than 5, so the result here is false, and it is not going to execute this code block. And it goes on and check that if this condition is right, if this condition is correct and true. So it says that 3 is smaller than 5, and it says that, okay, it is true, and I will just execute this code block. We can have lots of other lines of code. For example, print my name is Mohammed. So there is not a limitation, there is not a limit in how many lines can we write after the if and elif. So you can just have this part. So okay, let's go to another thing. We can have for loops. If we want to have loops, we have two options. We have a for loop and okay, and we have let me write it here. We have a while loop. So while loops and for loops, there is some differences between them. For example, I declare something for I in range. So in range is going to create some numbers. For example, if I type just 10 here, if I print the value of I, we see what's going on here. So the first number is 0 because the indexing in Python is starting from 0. So, but you see, we type 10, but the value here it is shown is 9. So Python do the indexing like this. For example, if I have a list, let me just say if I have a list, my list, for example, and let's have some, for example, apple, oranges, and bananas. Okay, and for example, cucumbers. Okay, so this is a list. This is a list of items. A list can accept any kind of data type. For example, I can just type here 5, 2, 5, 1, or a floating number. What is a floating number? A floating number is a number with a decimal point. So for example, 1.2 is a floating number, but 1 is a whole number. We called it integers. So we call this floating numbers or floats. We call this integers. So we can have all of these, or we can have something, for example, true, everything. So I'm not going to make it complicated. Let's stick to just some integers, as here integers are we know integers by just quotation mark or double quotation mark. For example, my name and my name is, for example, I can just put a quotation mark, or I can just put double quotation mark. So that's it. And if a list, I want to, let me just make it correct. So if I want to access, for example, oranges in this list, I'm going to do indexing. So for example, indexing is this. In a bracket, so in a square bracket, I just type 1. It says that index number 1, and we know that Python start its indexing from 0. So we are going to have the oranges. Okay, if we want bananas, we are going to type 2, index number 2, so bananas. And index 0 is this, apples. What if we want the last item, but the list is too long? For example, something like this. And for example, some random things. And we don't know, or we cannot start to count the numbers. For example, we don't know what is the index of cucumber. We just type here and enter -1, and it is and the result is the last item in that list, as you see here. So, but what if we want, for example, oranges and bananas, and we are going to do a slicing, as we called it, a slicing. For example, we know that the index here is 1, so we enter here in 1, and after that we place a colon here, and for example, from oranges to APPP. So this is index 1, 2, and 3. So let's just type 3 and let's see what's going on. So, but the result is just oranges and bananas. What happened to this? So this is index 0, index 1, index 2, and index 3. And we have entered number 3 here. But what's going on? Because Python do the indexing for the first number, as we have here, number 1, we entered 1, index 1. It is inclusive, so it includes the first index as we have here, but it is exclusive for the last item. So it just excludes it. It doesn't include the index 3, the last index, the index that stops there. So as you see here, I just explain it to know, so you can know what's going on in a range function. This is a function, and print is a function. We can know that what is a function. Functions have some parentheses and some arguments. So this is an argument, and we have some parentheses, and they have a color, like for example here, like kind of brownish color. So we know that it is a reserved, or it is a special word for Python. It is some kind of a built-in functions. We can define some functions, and we are going to see how, but not now, because we don't have enough time. It is a two-day workshop, and we are really short on time. And so you know here, because there are 10 numbers here, but because of we start from 0, we do not see number 10. So it is exclusive. It is like we say, for example, 0 to 10, range from, you start counting from 0 to 10, but we don't just type 0. So after that, it goes like a clock. So for example, let me just share my whole screen, and you can see that. For example, if, let me just draw it. Okay, can you see the Paint application that I just opened?
Yes.
Okay, so a for loop is like this. For example, this is our for loop. So a for loop, for example, in this case, is going to be executed 10 times. So the first time, I is equal to 0. So as we see here, and it goes on like this, as a clock, for example. So 0, and it reaches here, and it becomes 1, and it goes on, and 2, and it will goes on until it reaches its limit that we set to 10, to number 10. So after all, we see something like this. So what is a while loop? So a for loop is going to do this thing. It will iterate through the items of a list, a range function, or a dictionary. We have something like dictionary. Dictionaries are like this. For example, my dict is, we have some curly brackets, you see, and dictionaries have some keys and values. So for example, the key here, so for example, first key, I called it first key, so you know what's going on. For example, Mohammed, I will give it a value of a string value. So it is, for example, my name. So the first key is that, and the second key, for example, say second key. Second key is going to be, for example, I don't know, David, maybe. And as in list here, we can do this thing for them, or we can just say, for example, if we want the value of the first key, we can just have for example, this first key. Let me see what's the first key. Is there any kind of error in here or not? Let me see. First key is not defined. For example, this. I think it is reserved, yeah? Okay. Let's go on because I don't want to just debug this. So a while loop. A while loop, we have something like a while, and it will going to be executed until it reaches the limit. For example, while I is, for example, is smaller than 10, print hello. So, for example, I is like 0 here. So it will do the same thing, but here we don't want to just return the value of I. We just want to see the value of hello 10 times, for 10 times. So it will print this, but sometimes we should be aware that while loops, it doesn't become an infinitive while loop, because it goes it is going to be executed for forever, like forever. So you should just like you just choose something that is appropriate. For example, in here we have some kind of an infinitive loop, because whenever it is executed, we just initialize the value of y equals 0. So it is always smaller than 10. So it will be executed for forever. So we should be careful with these kinds of while loops. So I'm not going to run this because it will just it will crash. So it is not okay to run this thing. But what if I say, for example, I plus equals, or let me not just write like it like this, so it is easier to understand. So what we have here is just updating the value of y every time it iterates through the i's. So if I just let me just comment it out and to see the result here. So you see here, we just see hello for 10 times because it is going to be updated. So every time, for example, if I print I, so every time I is going to be like this, 0, 1, 2, 3. So every time it will update it by the value of 1. I can do, for example, value of 2 or whatever I want. But what if I don't just I'm not going to update the value of I, so it is always 0 and it is always smaller than 10. What will happen is like this. So you see, it is running, it is keeping running. So we have lots of these things. So we should be careful with using while loops, because if we don't have an updating statement here, so it will keep running and it is not good. Sometimes it will crash. And if you use Python inside Grasshopper, Grasshopper is not a very powerful kind of tool. So it will going to freeze your system or your machine and the application, or maybe you lose something. You should be careful about this. So Let me see what else I can tell you. The numbers here, the things here. Okay, and let's just maybe other things. We don't have lots of times. I think we should just skip what is going on. So okay. Let's just say okay, I think it will be fine. And let's just go to the slides that we have here. And okay, so let's see what's the timing here. Okay, and you can contact me through my email if you have any question, or you can just send me a message on Discord. I think it is more convenient to message on Discord for you. You can choose the way you want to send a message, and I will answer it as soon as possible. So this workshop, we are going to be getting some background knowledge about AI, machine learning, deep learning, and the differences about that, and some fundamental concepts. For example, tensor. What is a tensor? What is a matrix? What is a tensor in terms of, for example, how can we use these data and the data sets we have? How can we process them? How can we train a model? And we are going to do these things by practicing and some hands-on examples. So those files on my GitHub, you will use them through this workshop. And after that, I think tomorrow we are going to use a StyleGAN 2. So it is more exciting. Maybe the first day is a little boring because most of it are some kinds of codes or theories or the concepts behind AI. So, but tomorrow is really exciting. And please have a Colab Pro subscription so we can work on the files. So you see, let me just have it like that. And okay, you see, artificial intelligence is like a bigger area, is like their boss, for example. And machine learning and deep learning are the subsets of artificial intelligence. So, but nowadays, the most of the talkings are around deep learning or generative adversarial networks. Generative adversarial networks are a part of deep learning. So that's it. And let's say what's going on. Okay. A short history about artificial intelligence is like AI was born in 1950s, and if I want to be accurate, it was 1956, around that time. So the effort was to automate intellectual tasks that normally performed by humans. So AI, the idea behind AI was this. So a question for AI, of course, it is a question for intelligence. So we are going to questioning intelligence. And what is intelligence? AI is like a general field that just that encompasses a machine learning and deep learning, but that also includes many more approaches that don't involve any learning. So it is not just about learning something. The algorithm is not going just to learn something. Either there are other approaches to AI, but we are focusing and we are going to work just on deep learning and machine learning. So early chess programs, for instance, only involved hard-coded rules crafted by some programmers and didn't qualify as machine learning. For a fairly long time, it was for a fairly long time, many experts believe that human-level artificial intelligence can be achieved by having programmers handcraft some sufficiently large sets of explicit rules for manipulating knowledge. This approach is known as symbolic AI. So it was symbolic AI, and it was dominant paradigm in AI from 1950s to the late 1980s. So it reached its peak popularity during the expert systems boom of the 1980s. So you see what's going on here and the history behind AI. So AI is not something, for example, from yesterday. So it was born around 1950s. And although symbolic AI, let me say, proved suitable to solve well-defined some logical problems, such as, for example, playing chess, it turned out to be intractable to figure out explicit rules for solving more complex problems. For example, image classifications or speech recognition, as we call them, natural language processing, and some other things. For example, language translation, for example, Google Translate. It uses AI and lots of data. Google has a lot of data. And, you know, they have access to our data, our own data. We use our phones, our computers, the internet, we search the web, and they just store that data in their databases, and they use it to train their models. Maybe sometimes they use it against us, maybe sometimes they use it for some beneficial things. So it is some kind of an ethical question. It is a moral and ethical question. So what we are going to do here, most of the parts are around image processing, image classifications, image generating images. So most of our thing is about images. So we know our problem, and we know our thing now. And for example, what some new approaches arose to take symbolic AI's place, and it is called machine learning. So what we have here is machine learning. And for example, these people, Ada Lovelace and Charles Babbage, and they were some kind of, they were the inventor of the analytical engine, so as they called it, the first known general purpose mechanical computer. But it wasn't meant as a general purpose computer. It was designed in around 1830s and 1820s, I think. So it is just for doing some basic things, basic materials, basic math problems, to solve those kinds of problems. So you know, after that, we know someone he is very famous and he is very popular in this field, Alan Turing. And I think most of you watched the Imitation Game. That movie was about Alan Turing, and in 1950s he published a book that was called Computing Machinery and Intelligence. So it was really he was really a pioneer, or he is like a father to the machine learning and AI field. And there is something that we call the Turing test. The Turing test originally called the imitation game by Alan Turing in 1950. It is a set of machines' ability to uh, exhibit intelligent behavior equivalent to or indistinguishable from uh, behaviors of a human. So if we cannot distinguish the behavior of a machine from the behavior of a human, so that algorithm is going to pass the Turing test. So it is a very important test that Turing has developed. And Turing was quoting that Ada Lovelace, while pondering whether let me remember his exact words, and it was while pondering whether general purpose computers could be capable of learning an originality or creativity, and Turing came to the conclusion that they could. The machines are able. And let me just have it. No. And so at that time, it was really shocking, or it was really amazing that some people can, like Alan Turing said, that machines can learn, machines can do something creative, as we see here nowadays, for example, generating some images or generating some faces that they don't exist, and something new. Or for example, Lisa, an AI algorithm that he lost to that algorithm. And but what is machine learning? And machine learning, the question about machine learning, and that question of Alan Turing opens the door to a new programming paradigm. In classical programming, like here, we have some rules and data, and the algorithm produces some answers. So they are hard coded, and they just do something, and we know how they are doing it. But now it should be machine learning, this part. So now we just give machine learnings or AI algorithms data and answers, and they will generate the rules for them. They will learn the patterns behind it. So for example, Google Photos, for example, most of us use it for just categorizing our photos, for example, vacation pictures, and Google Photos just put some tags on them. It just uses AI. Although machine learning only started to flourish in 1990s, around that time, it has quickly become the most popular and most successful subfield of AI, a trend driven by the availability of faster hardware and larger data sets because of the emergence of the internet. So there are lots of data we can use, for example, Instagram, Facebook, images, YouTube, videos, everything. Arc Daily we use every day, or plans, those kinds of architectural plans that we see in every book. They are data sets. We can use them to have something new, to have something creative. So, and faster hardware is like, for example, GPUs. GPUs are really powerful. So if we have access to powerful GPUs, we can use them in a good way and in our algorithms in AI. So let's go on. And sorry. Just for example, let me here. To do machine learning, we need three things: input. For instance, if the test is an image classification, these data points, the data can be like images of people or images of buildings, images of the interiors of some buildings. So the task is something like image generating or synthesizing images, creating new images. And examples, we need another thing, the examples of expected output. So we called expected output, we called it labels. So we are going to input, we have input and we have labels. X is going to be input and Y is going to be the labels. So a way to, and we need another thing, a way to measure how well it is working, how well the algorithm is learning and working, so everything is fine. We need some kind of a measure, so everything is fine. We know how good it is working. And there is something in machine learning, and the difference between machine learning and deep learning is in machine learning algorithms, we need to extract the features of our data sets. But in deep learning, it is not necessary. We don't have to do that. The algorithm itself is going to do this for us. So it is going to be something like, for example, like this. The raw data are these data points, and we are going to just what we do, or what AI is going to do is going. We are going to fit a line between them. For example, we have some. Yeah. Okay. We are going, for example, to draw a line between them and separate these data points, but it is not. But sometimes the data set is really complex, so it is really complicated. So we cannot just draw some line between them. We are going to use some activation functions as we are going to learn about them. And the deep learning. So the first thing, deep learning in a nutshell, I think maybe deep learning is a specific subfield of machine learning. So, you know, a new take on learning representation from data that puts an emphasis on learning successive layers of increasingly meaningful representations. So, for example, other approaches to machine learning tend to focus on learning only one or two layers of representations of the data. Hence, they are sometimes called shallow learning. So it is against, or the other side of learning, shallow learning and deep learning. In deep learning, these layered representations are almost always learned via models called neural networks. So we hear most of the time neural networks, but what are neural networks? We are going to learn neural networks and how they do their jobs and how they work. So the term neural network is a reference to neurobiology. So this is the kind of deep learning we are talking. Deep learning models are not models of the brain, as Francois Scholle said. They are not mimicking or they are not imitating what our brains doing. They are different in most of the way, but similar somehow. You can think of a deep learning network or a deep network as a multi-stage. So, you know, a multi-stage information operation where information goes through successive filters and comes out increasingly purified. So we are going to purify the data, and it is called the learning. The specification of what a layer does to its input data in here, it is a LUNet 5, the first deep learning network in the history. It is invented or created by Jan LeCun, who is the head AI engineer of Facebook. So he's working in Facebook nowadays, and he's one of the godfathers of deep learning of the world. So in this context, learning means finding a set of values for the weights of all layers in a network. The specification of what a layer does to its input data is stored in its layers weights, which is the essence of a branch of numbers. So we have the data and we have some weights, and we are going to just manipulate the weights. The algorithm is going to do this for us. So it will represent the data better. So to control something, first you need to be able to observe it. To control the output of a neural network, you need to be able to measure how far this output is from what you expected. So this is the job of the loss function. So we have the input, and it is going to go successive in the layers, and the weights. We have the weights, and we have some predictions. So we are going to predict something. The algorithm is going to predict something for us. And the loss function is going to say how far this output or this prediction is from what we expected, or the labels we have, or the ground truths. So the loss function takes the predictions of the network and the true target. So for example, let me just, this is the prediction and this is our labels. So the loss function takes the predictions of the network and the true target. And sorry, what you wanted, the net and and it will compute a distance score. So it is a single value, and capturing how well the network has done on this specific example. So this is how loss function is working, And after that, we have a loss score. It is just a single value. For example, 5, 2, 3, 15, everything. It is that kind of value. So after that, the fundamental trick in deep learning is to use this score, this loss score, as a feedback to signal to adjust the weights of a little bit. So in every iteration, we are going to use this loss score to adjust the weights a little bit, and to make the network learn better. So it will lower the loss score. So every time the loss score is going to be lowered, we are going to be happier. This adjustment is the job of the optimizer. Optimizer here, which implements what is called backpropagation. So backpropagation algorithm, the central algorithm in the deep learning. It is the most important part in this algorithm. So it will optimize the weights, it will update it, and the model is going to get better every time it optimize the weights. So sorry, initially the weights of the network are assigned random values. So the network merely implements a series of random transformations. So this is the training loop, which repeated a sufficient number of times and iterations, maybe, for example, over 1,000 times, over 10,000 times. It depends on the situation, and yields weight values that minimize the loss function. And a network with a minimal loss is one for which the outputs are as close as they can be to the targets. So a trained network is like this. And sorry, Although deep learning is fairly old subfield of machine learning, it only rose to prominence in the early 2010s with remarkable results on perceptual problems such as seeing and hearing problems such as that. So in particular, deep learning has achieved the following breakthroughs, all in historically difficult areas of machine learning. For example, near human level image classification, we are going to see the percentages, and you are going to be uh, shocked. They are really good. They are really great. They do it really good. Or near human level of speech recognition, handwriting transcription, as for example, you type something on your smartphone screen and it knows what you type. So it is amazing. Improved machine translation, improved text to speech, or uh, something like that. Or for example, when you go to Amazon, to the Amazon web store, they know what you need. They suggest you what you need, and it is like that. This is magic. How could they? But they have lots of data. For example, they know what you are doing on your Facebook, on your Instagram. They have a lot of data about you, and uh, they need that data because data is like money and power to them, so they need it. But we have uh, some uh, for example, let's say Marvin Minsky here, human level of AI. So talk of human level general intelligence. So as some called it AGI, artificial general intelligence, shouldn't be taken too seriously. The risk with high expectations for the short term is that as technology fails to deliver, research investment will dry up. So slowing progress for a long time. So we have two winter AIs between 1960s and early 1970s and around 1990s. So uh, it was like a dry up. So the investments has gone, and there were no investment in AI. So we should just not overrate AI, or we should not just expect too much from AI. Someone think that AI is going to do anything. If we say, please, AI, do this, and they are going to do whatever they want. We should know the limitations, we should know the scope, and we should know how they work. And we should know the base and the fundamentals of it. For example, how a network is built up, how a network is created, how we can use it. Sometimes you have something amazing in mind, but uh, AI cannot help you with that. It is not. You should just expect something that AI can handle for now, because maybe a year from now or 2 years from now, AI is going to be something super amazing. We don't know. Maybe an algorithm is created and it can do everything. We don't know. But now we should just expect something that it can handle. So it is good to know these kinds of things. And we should just see the bigger picture. For example, Siri on iPhone can interact with us, or we see Joaquin Phoenix, yeah, on her movie. He fell in love with an AI assistant. So something like this maybe will happen in the near future. And we should just not overrate AI. We should just expect something logically or something rationally. So before deep learning, we have, for example, we had, if deep learning is your first contact with machine learning, so then you may find yourself in a situation where all you have is the deep learning, all you have is the deep learning hammer, and every machine learning problem starts to look like a nail. So the only way not to fall into this trap is to be familiar with other approaches and practices and practice them when appropriate. So, but we are not going to focus on that. We are just going to talk about them a little bit so you get familiarized. For example, probabilistic modeling is the application of principles of statistics to data analysis. It was one of the earliest forms of machine learning, and it is still widely used to this day. One of the best known algorithms in this category is the naive Bayes algorithm. So naive Bayes algorithm is a type of machine learning classifier based on applying Bayes' theorem while assuming that the features in the output data are all independent. And we have logistic regression that is a closely related model to a closely related model is the logistic regression, which is sometimes considered to be the hello world of modern machine learning. Don't be misled by its name. Logistic regression is a classification algorithm rather than a regression algorithm, you know. And we have here Jan LeCun. This is one of he is one of the godfathers of deep learning. So he created LUNET 5 in 1989. So you know, that's amazing. He invented LUNET 5 for American post authorities. So they wanted to send some mails, and they wanted to just give the algorithm some images of the digits on the pockets of the mails, and the algorithm should just recognize the digits. So this man invented something that he called LUNET 5, and it was amazing because in those days, back to those days, it was like magic. So, you know, although the core idea of neural networks were investigated in toy forms as early as in the 1950s, this changed in the mid 1980s. So when multiple people independently rediscovered the backpropagation algorithm, as we discussed earlier a little bit about backpropagation. Backpropagation is a way to train chains of parametric operations using gradient descent optimization. And the first successful practical application of neural networks came in 1989 from Bell Labs, when Jan LeCun combined the earlier ideas of convolutional neural networks and backpropagation and applied them to the problem of classifying handwritten digits. The resulting networks, dubbed LUNET 5 or LUNET, was used by the United States Postal Service in the 1990s to automate the reading of zip codes on mail envelopes and pockets. So we have other kinds of algorithms that were before deep learning, as we called several kernel methods, or a subset of kernel methods is supported vector machines. So the data is mapped to a new high dimensional representation in these kinds of algorithms, as we see here. For example, let me just, okay, so as we see here, the problem is really twisted or complicated, and the data is mapped to a new high dimensional, for example, this or that high dimensional representation where the decision boundary can be expressed as a hyperplane, and this yellow hyperplane is the decision boundary if the data was two-dimensional, of course. So a good decision boundary is computed by trying to maximize the distance, as we see here, maximize the distance between the hyperplane, the yellow plane, and the closest data points from each class. This is a data point from class red, and this is a data point of class blue. And he's Sam, he's Joe. So we just want to maximize the distance between the hyperplane and the individual data points of each class. This step is called maximizing the margin. So this allows the boundary to generate well-to-know samples outside of the training data set. So, sorry. We have other things like decision trees, random forests, and gradient boosting machines, but we are not going to talk about them because we don't have enough time to talk about them, and it is not really necessary because we are not working with them. But back to neural networks, around around 2010, there was a breakthrough to the deep learning and to the ImageNet competition in 2011. And these people, this is Jeffrey Hinton. He is a professor at the University of Toronto, and this is Yann LeCun at University of New York, if I'm not mistaken, and this is Yoshua Bengio. So these three people are the godfathers of modern deep learning. They are the godfathers of deep learning. So they are the pioneers. And this guy is Alex Krzyzewski. He was a doctoral student of at the University of Toronto. His supervisor was Jeffrey Hinton, and in 2011, as you see here, the percentage of the ImageNet classification error and top 5 errors. So humans have just 5% of error. So they mistake 5% of the time in ImageNet classification problem. So image classification is like a data set of 1,000 classes, and each class has around, I think, 1,000 images, so or more. So it is like a million or more than a million images in ImageNet. So there were some kind of networks, some AI networks that were doing like 26% of error. So, but it was in 2011. So, but in 2012, this person, Alex Krzyzewski, made another neural network to classify the images. So all of a sudden, we see a decrease in error. So the performance got better by 10%. So it was really a huge breakthrough, 10% of better in performance. So you see, and he uses deep learning in his network after that, and convolutional neural networks. We are going to know what is convolutional neural network and how we can implement those kinds of things. And after that date, every time and in each year, they were using neural networks and convolutional neural networks, and each time they were just doing better, as you see here. And in 2015, ResNet is created by Microsoft. So it is an algorithm, an AI algorithm, deep learning algorithm that is created by Microsoft, and it is better than what humans do in image classification problems of ImageNet. So, and after that, GoogleNet, or Inception, as they call it, it got better, better, and better. And now we are in 2021, 5 years after 2016. You can imagine how good and how well convolutional neural networks and deep learning algorithms are working, are doing their jobs. Sorry. Uh, so what makes deep learning this special? So there are some reasons why deep learning is really good. Deep learning architectures or models are really good because deep learning offered better performance on many problems. So we can scale it to many problems. And it makes problem solving much easier because it completely automates what used to be most crucial step in a machine learning workflow: feature engineering or feature extraction. As I told you here, uh, there is no need to do the feature extraction in deep learning, so it does the job. So back to this. Okay, so it does the job. And um, feature engineering, if I want to explain it, and people or scientists or AI researchers had to manually engineer good layers of representations for their data. This is called feature engineering. And deep learning, on the other hand, completely automates this step with this step. So deep learning is that it allows a model to learn all layers of representation jointly at the same time rather than in succession. So it is called greedy, greedily greedily learning. So it will learn the data at the same time rather than in succession. With joint feature learning, whenever the model adjusts one of its internal features, all other features that depend on it automatically adapt to the change without requiring human intervention. So it is going to get be simpler. So it is going to be simpler, you know. Everything is supervised by a single feedback signal. Every change in the model serves the end goal. So the loss function uh, is going to supervise the whole network by just using back propagation and optimizer, you know. In conclusion, incremental and deep learning is incremental and layer by layer way in which increasingly complex representations are developed. So these intermediate incremental representations are learned jointly. In 2016 and 2017, Kaggle is a website for data science and data science competitions, and uh, you can download some data sets on that. Kaggle was dominated but by two approaches. First, gradient boosting machines, and the other one was deep learning. So specifically, gradient boosting is using for problems where structured data is available. But deep learning is used for perceptual problems such as image classification and image generation. So you see, but why now? Why now we use deep learning? And because of better hardware, hardwares as GPUs, as better GPUs we have, and they are available, or the data sets and the benchmark, because of the big data, because of the internet, we have lots of data. The scarcity of data is really good, and some algorithmic advances. The advances in algorithms were better activation functions that we are going to learn about it, and better weight initialization schemes, starting with layer-wise pre-training, which was quickly abandoned, but better optimization schemes such as RMS prop and Adam algorithms. and we are going to learn all about them. So we are going to through some democratization of AI nowadays, and back to for example 10 or 12 years ago, they use C++ or Java or other languages, but nowadays most of data scientists or AI enthusiasts, AI researchers, AI pioneers use Python, because Python is really simple, so you can just implement what you have in mind really quickly. So you can just write the code, type the code, and so it is really fast. It is really easy to understand. And why we use Nvidia GPUs? Because Nvidia has introduced some language, some programming language that is called CUDA, and we have some CUDA cores, and they just facilitate deep learning, AI, and the implementation of these algorithms. And nowadays, it is like the standard of hardware. So if you want to run the codes locally, you must have an Nvidia GPU. So for example, let's go to some classification, and let's see what is a classification, for example. And let's start with MNIST dataset. MNIST dataset, let me just okay, so okay. Can you see my screen? Is it okay?
Yes.
Okay, so I'm going to run the Jupyter Notebook locally, but we can have a session of code, so it's fine. But I'm going to run it locally, and let's see what was the MNIST classification. Okay, so let me find the appropriate notebook here. Lunet 5 with cross, basic regression, CNN. Okay, I said okay. So let me set the kernel here, because I have done something special to the kernel, and let me just move the zoom controls, and here we go. You don't need to know what I'm doing here. I just explain it, and we are going to explain it in depth in the upcoming minutes. But now, just I want you to know what's going on here. So let me see. So for example, we are importing the libraries we want, as you see here, TensorFlow, and from TensorFlow Cross. And Keras is nowadays a part of TensorFlow. So, but for example, I remember 5 or 6 years ago, if I'm not mistaken, Keras was like something extra, something that facilitate the workflow, but it was not a part of TensorFlow. But after a conference that was that Google announced that now cross is a part of TensorFlow, and it is a good thing to have cross as a part of TensorFlow. So we have optimizers classes, and we import Adam. Adam is an algorithm in optimizers, and we have Numpy. Numpy is a library for doing a statistical for solving statistical problems or doing some math problems, some basic things. So it is, but it is really fast. It is like the standard of scientific programming, one of the standard libraries of scientific programming. So as you see here, I import MNIST dataset. So, and if you don't have the dataset, it will download it for you. For example, if I want to show you where is the location and user, and this one, and Keras. So this is .keras in your user. You see it here. If I go to the datasets folder, I have, for example, these datasets. Fashion MNIST is another dataset, MNIST, Reuters, and other things, Cypher 10, other things. So it will download it. And what we have, what I did here is just because the MNIST dataset is like some integers, you know, from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, and 9. And the background is black, and the digits are white, are in white. So we know that, for example, most of you have worked with Photoshop, and we know that the color range is from 0 to 256. So what we see here is just dividing each value of each value of x's of our data set x by 255, because we want to normalize the values, and we have values from 0 to 1. The interval of the values will become this, because the maximum value of each pixel in each image is 255, and the minimum value of each pixel in every image is 0. So the interval of the pixel values is going to be normalized between 0 to 10. After that, and we are going to just have the first 5,000 images, because MNIST dataset, I think, have 60,000 images. So we just want a portion of that dataset. We are going to create our model, our architecture. So we are going. I'm not explaining it now, because we are going to learn what they are in our next slide. So don't worry if you don't understand what they are. We are going to be familiarized with that. This is our architecture, the architecture of the model, and we compiled it. And the optimizer is Adam, as we have imported it here. And the loss function is a sparse categorical cross entropy. We are going to learn what it is. So this is just an introduction. Don't worry if you don't know it. And the metrics is accuracy. So accuracy is like is the measure for how well the network is doing its job. After that, we fit the model, we fit the x and y's, the labels and the inputs. X is the input, and y is the output, is the labels. By 5 iterations, the epochs is the iterations, and 5 iterations. And we have some validation data. And in the end, we see that validation accuracy is like 99%. So 99 is like a real high accuracy. And so this architecture with just 5, I think, yeah, 1, 2, 3, 5, 4. Okay, with 5 layers, this 5-layered neural network is really powerful enough to classify these images, the MNIST data set. So I just don't run this, but if I run these cells, because they are not too heavy or too weighty, it is going to be really quick. But sometimes they take a lot of time to do this. For example, you see, it is just a matter of seconds, and I just run this cell, and let's see what's going on. And after that, at last, in this part, we evaluate and we measure the performance of the model on our test data set, because we have a trained data set here, and we just divide them, the trained data set, input, train, and labels of the trained data set, and input of the test data set, and input input of the test data set and output of the test data set, the labels here. So, and we have just 5,000 of them, not all the whole data set that contains 60,000 images. So you see how quick it is fitting, it is running. It in the first iteration, it just took 25 seconds, and the other iterations just 14 seconds. So because you know, black is like 0. If we normalize the value here, it doesn't have any value, it is 0, and white is equals to 1 or 255 or 1, because we want to normalize the value. So as you see here, it is nothing really special nowadays, but those days when Jan LeCun developed this in 1989, you can just you see how great is this. But nowadays, the models, the deep learning models, are really powerful enough to do these. This is simple. This is easy for them to just classify these kinds of problems. So, and we evaluate this, and on our test data set, the accuracy is 98%. So it is really high, you know. Sometimes it is like overfitting. We are going to know what overfitting is. So what is this? Okay. So let me say something. And Jupyter Notebook, as you see here, this is a Jupyter Notebook. So let me just put the zoom control here. And so as I said earlier, you can just hit Control Enter to run each cell. So the cells are independent, so you can run them independently. For example, if I just have some, for example, x plus y, let me say x plus y, and we have another cell, for example, x5 and y10, we just have this, but we can run it independently. For example, if I, and let me say something like this. And let's give another value to x, for example, and we see here that x is like this, and the result is 16. But here the result is 15. They are independent. But if let me just do it. You see, if I just erase the x newer value, they are working with each other, but you can run them independently. So let's just delete these things. And sometimes you want just to write something. For example, you want to write my name is David. So, but you know that it is like a code here. It recognizes this cell as a code. You can just go there and say that it is a markdown, for example, and run it. So it is a markdown. It is not treated as a code cell. So, and you can download this in different formats, as you see, and you can save it or make copies or new notebooks. But we have something as a kernel. Our kernel is now Python version 3. As I said, it is better to install or to have Python version 3.7 or 3.8. And we have other kernels here too. So we can just have other virtual environments. You can just, for example, you can just virtual environments. It's better if you want to install, for example, these libraries or these packages on your local machine. It's better first to have some virtual environments because they are independent. They are working independently. If let me show you, for example, conda if list env. I think this is the command here. Let's say if it is. End list. Let's see. And list, I think. Okay. Okay, so as you see here, this is the command. I have 2, 4, 6, 7 different kind of virtual environments, and most of them have different versions or different kinds of packages. For example, I have PyTorch here and PyTorch, another type of PyTorch, and I have TensorFlow. I have another environment for my Pix-to-Pix generative adversarial networks, and I have another type of thing for just working with data frames and pandas package, and some other things. It's better not to install most of your packages on your base environment. Please create some virtual environment first. You can just, as you see here, managing environments. You can just, let me just send you this in the chat box. So we can just, for example, creating an environment with commands, and it will, you are going through the instructions, and you will create new environments, for example, and it will help you with creating new environments. So, and let's get back to what we were saying here. Let me just this and there. Okay. So we have different data representation. Let me check what time it is. Okay, we have 11 more. Yeah, we have 11 more minutes. We will go on a break at 12 o'clock. I will just explain this part, and we will have our break time. Okay. Okay. So let's go on. And so what was I saying? So what is a tensor? Tensor is like the base form of what we are going to work with, you know. Base tensor is like a container for the data, almost always numerical data. So the context of tensors, a dimension is often called an axis. In the context of tensors, a dimension is called axis. So a tensor is defined by three key attributes. The first the first attribute is number of the axis of the, or the rank of the tensor. For example, 3D tensors has 3 axes. For example, in Numpy, you can just let's go back to this part, the introduction to Numpy. So, okay. For example, we have Numpy here, and Numpy is going to do some statistical operations. So, for example, we have an array, a Numpy array, and we feed our networks Numpy arrays, not list, not images, because it cannot understand what is an image. An AI cannot understand what is an image. They just know numbers. We should just give them numbers, for example, as we hear, and we should just give them Numpy arrays in TensorFlow. So you see, let me go through it. And for example, if I just do it, you see, I initialized A and it is a Numpy array. And if I print its type, and it will return the type of that array, and it says that it is a Numpy ND array. ND array is meant that it is n-dimensional array. So let's do it. And you have, if you see here, we have if I print the shape of the A is the Numpy array of 1, 2, 3, the values of 1, 2, 3. It says that it has just an axis. It is the tensor here is rank 1 tensor. You see, we have just one axis, and the axis has 3 values. You see, 3 values in an axis, so it is like a vector. So after that, let's just go through it and let's see. And if I print the first index of A, it will print 1, as we see here. If I print index 1, it will print 2, as we see here, and so on. So what if I just change the first index of A to 5, and print A here is going to return the value 5. So they are mutable. We can change the values, you see. And here is the B. B, if I just print the shape of B, it is going to be like 2 and 3. It has two axes. You see the first axis and the second axis. The first axis is like this. You see the 1 and 2. This is 1 and 2. And in each column, we have 3 values. We have 3 values in each column. So that is like that. So Numpy also, for example, if I just do this, you see, I import Numpy as NP. So I aliases that I give it a simpler name to use it, and I have not to, every time I want to use Numpy, I have not to type NumPy its full name. I just type np dot zeros, for example, and it will create an array that is all zeros, and the shape is going to be 2 by 2. You see here 2 by 2, 2 rows and 2 columns, 2 rows and 2 columns. So, and for example, if I this is 1 row and 2 columns, but the values are 1. So this function will return all ones, and the shape of that is going to be like this. You see, we have 2 brackets, square brackets. So an NP full, for example, you can have this. NP full is like this. We give it the shape of the tensor and the array, and it is 2 by 2, 2 rows and 2 columns. And the value we want, for example, we have, if we want 1, just all of them are 1, I can do this. It is like if we want here as 1. You see, for example, you see, this is like that. This is like that. But what if we want other values? For example, we can have 7. So let's say, and this is this will return an identity matrix. You know that matrix, identity matrices are like that. They have just one values, ones on their diagonal axes, and other parts, their other parts are just zeros. So you can go through this, and you can see what we can do with NumPy. And array indexing, as we called, and for example, this is 3 by 4. We have 3 rows in here, and we have 4 columns. You see, it is like this, as I type it here for you. And what if we want some specific values? For example, this here, and for example, I want 0. I want row from 0 to 2, and the column from first column 1 to column 3. So this will be like this. So let me print B. Oh, sorry. Print B, and this will this is going to be like this. Let me just have it here and have it here, because I changed the value here, as you see. That's why it has some ridiculous numbers here. And let's see what it will it returns. You see, we do some array or list indexing, but just giving its indexes, giving it some indexes. So we can have other things like this. You can go through this. I'm not going through this a lot, because we are short on time. But NumPy is really fast and really is really a great library. So we have Boolean indexing. You can index it, but by Booleans. For example, the result of this comparison is a Boolean. For values greater than 2, it will return something. For example, false, false, true, true, true. Because if I let me just this, you see here. So I print the Boolean indexes here, and it returns this for this thing. So you see, the false values are like this. But what if I want to have just this one? Or I can say this is a variable. I called it bool IDX or indexes. And what if I want just the part of a array that are bigger or greater than 2? So it will return those parts. So let me just comment it out so you can see, and comment this out. You can see that I just do some Boolean array indexing, and I can just rewrite it in this way. So we can have it as this is, and they are going to be the same. You see, they are the same. And data types, for example, if I create another array, Numpy array in here, an array is going to be, for example, 1, 2. So a small array. So if I type x.dtype, it will return something integer 64. Integer 64 is something, special kinds of integers. You can read about them if you want in here, or you can search the web if you want to know more about integer 64, but it is not really necessary. You should just know this thing, x.dtype. It will return the data type of that array. You see here, because I have floating numbers, it will return float 64. Let me just correct it, I say. So, for example, when we are creating or initializing an array, we can tell Numpy what kind of data type we want from it. So, as you see here, I said that the data type should be integer 64. You see? And what if, for example, integer 16, if I'm not mistaken? And you see here, it is integer 16 and integer 64. Okay, it is integer 64. You see, you can do some basic mathematical operations, and it will do it element-wise. You see, we have, and they should have corresponding elements. They should be element-wise. So, for example, I cannot have different shapes and different sizes, different arrays with different sizes, and do mathematical operations on them. So it is not possible because it is not logical. It is not rational, you know. And it will just, as you see here, for example, if the array is like this, array X is like this, and array Y is like this, the result of X and Y is like this. So in these kinds of simple arrays that we have just 4 elements here, it is not really it is not a real big difference between using, for example, X plus Y or np.add X and Y, because np.add X and Y, I was watching some video on YouTube, and it is, Numpy is really fast, and we are going to see the differences if the arrays are really big enough. For example, big arrays are going to show the power of Numpy. That's why we use Numpy in artificial intelligence, in TensorFlow, in creating AI algorithms. So you can just go through it. We can multiply, subtract, square root. Okay, let me check what time it is. Okay, we are going to have our break time, and we are going to be back at 1 p.m. New York time. So let me say it, 1 p.m. Okay, we have 1 hour to rest. So that's it. If you have any question, you can ask, or we can just go to our break. So I think
Well,
we
I
have.
have many,
And I will not ask though, because I have many. So it's better to have a break.
Okay. So let's have our break, and I will be back in an hour.
All right, thank you.
Sure.